doing handicaps first. Yes, we'll start with a handicap hypothesis because it came first in time. So we owe the handicap hypothesis to this wonderfully irascible Israeli biologist called Amotz Zahavi, who sadly died recently. It was very, very sad. But his handicap hypothesis was the idea that in order to be an honest trait, the indicator must be something which is costly to maintain. So the idea is that the trait, as I was saying for carotenoids, the trait signals that you have so much of this resource, whatever the resource is, you have so much of an important resource that you're able to squander it on an indicator. And the idea is that low quality individuals are not able to bear the cost of production of that signal. So the trait is an honest indicator because it is costly. And that's, that doesn't specifically make reference to things like parasites and abiotic conditions, etc. It says this trait is simply costly to maintain. And that was modelled by Rufus Johnston. There have been a number of different... Amotz Zahavi basically just pushed this out in the world and went, it works, I'm going home now. And subsequent researchers have made a lot of different models based on tiny little details of the idea about how it should work. But one good one, which is reasonably easy to understand. Some of them are really involved and really mathematical and dense, but one which is relatively easy to understand is Rufus Johnston's model of a handicap, where if you can imagine the signal intensity, i.e. the size of the trait, the length of the tail, etc., along the y-axis. How long is your tail along the x-axis? And then we're going to do one of those marginal value models. So costs and benefits are up the y-axis. So thinking about the benefits first, the benefits of having a longer tail are going to involve more matings and getting more females. But there's only so many females in the environment. The more females you've already mated with, the fewer there are to find in the environment. There's going to be a point where there just aren't any more females to be successful with. So there's going to be diminishing returns. And also there's going to be viability selection as well. So, the longer your tail, the benefits of having a longer tail kind of asymptote after a while, because there just aren't any more females. Once you've mated with every female in the population, then there's no more benefit to having a longer tail. Now consider the costs. So the costs are going to increase in a fairly linear fashion, and for a high quality male, the costs of having a longer tail, like increased mortality, etc., it's heavy, you can't drag it around, it's hard to fly with a longer tail. And for each increment in tail length, those costs are going to increase in a fairly linear fashion. Like having a ridiculously long tail as opposed to merely a stupidly long tail is not going to get you very many more females, but it may well render you vulnerable to more predators, for example. So those costs are going to increase linearly. And to a high quality male, the optimal tail length is then one which gains you the most females for the least cost. So the best signal intensity for a high quality male is here. That's the point at which the benefits most outweigh the costs. Benefits minus costs is maximized. But then if you imagine a low quality male for whom the costs in terms of mortality of bearing that thing increase more steeply, consider the same calculation for a low quality male, and now the point at which the benefits most outweigh the costs is lower. So for a low quality male, it benefits him most to make a less of a signal. So you can imagine that this is going to distinguish between high quality and low quality males because of the cost of bearing the trait. So nice kind of marginal value theorem explanation for why handicaps might be reliable, honest signals in a population of males. One interesting spin-off of this, and we're going to hear a lot more about this from Domino's next lecture on Friday, is something called the Leck paradox, which is if females have unlimited choice, if females are in a situation where they can compare every male against every other male, there's no kind of spatial structure, and your choice is unlimited. You can always choose the best male, whatever happens. There's no cost for you to choose, for all females to choose the very best male. So if all females choose just the one male, then clearly Fisherian runaway is going to be very quick, and that trait is going to go to fixation very soon. And theoretically, it should exhaust genetic variation within a population. Like, why, if all females choose one male, why is there ever any variation in these traits at all? Why don't all males have the same tail length, which is directly at a viability limit? So why doesn't that? Well, Domino's going to talk about this. Is called the Leck paradox. And there are a number of different ways that it's resolved, why we think this doesn't occur. One of which, I'll go through one now because it pertains to these traits, but Domino will go through a few more in her lecture. Why isn't genetic variation exhausted? Well, yeah, the beans on that, obviously. One reason it isn't is because of the idea of a revealing signal. Now, we've just been through this. A revealing signal is the idea that you are constantly under attack from parasites and bacteria, microbes, parasites, etc. And they are very good at evolving. They tend to have much shorter generation times than we do, so their rates of evolution are higher. So we are just constantly under attack from these things, and it's a constant battle to keep maintaining our traits at a high level of quality. Not only is it a constant battle to survive against parasites, it's an especially constant battle to survive and also be beautiful. And so a revealing handicap, as I was saying, is something which provides a window onto the quality of your genes with specific reference to combating parasites. And that's Hamilton and Zooke's idea, that parasite load is what maintains secondary sexual traits at this kind of these conspicuous traits. Their specific prediction, and I wish I'd managed to I should include in future lectures. I will include a test of this prediction. I haven't managed to find one yet. But their specific prediction, which is really cunning, is that if you look across, if this is true, if you look between species, at different species and the brightness of their plumage, you would find that those species which have more parasites generally, the females gain more by choosing the brighter males. So basically, if you're in a species where males are really brightly coloured, you know that this is a species which is attacked by parasites because females stand to gain more by choosing a brightly coloured male in a species which is more attacked by parasites. Species where males are dull, and for males and females are both dull, are ones which don't really have a problem with parasites. Does that make sense? Yeah. But then, so that's among species. But then if you look at exactly the same traits within a species, take one of these species which is attacked by parasites a lot. If you look at males within that species, you would see the opposite trend, which is that males with more parasites have duller plumage. It's those males with brighter plumage that are able to resist the parasites. So they predict two opposite trends within a species and among species, which is a really beautiful prediction. And I'd love to see it. I'd love to see a study. Do you know of one?
I don't know of one that does both.
Okay.
Just to relate to the workshop on Monday, as all of this does.
Okay.
There is one study that's done this within a species in cichlids and finds that bower asymmetry is related to parasite range.
Oh, brilliant. Okay.
And so many
Cool. Okay, so for panopto purposes, Domino just pointed out that there's a study of cichlids, which we referenced in the workshop, that shows that within a species, the asymmetry of bowers is related to the parasite load of the male that's made the bower. So that's a very nice within-species demonstration. So the prediction there is if you look among cichlid species, species with bigger bowers would be the ones which are generally attacked more by parasites, or more symmetrical bowers at least.